Hi, this is Curtis Goodwin. Now for our second half of our final project for ADTA 5240, we're going to construct a well-defined schema in Hive. We're going to run a couple queries in Hive. We're going to run the same two queries in Spark SQL, and then we're going to compare performances between Hive and Spark SQL. So let's get going. So the first part of part 2 is we want to load data into the Google Cloud Platform cluster and construct a well-defined schema and then run two queries. So before this happens, we need to set up an HDFS subfolder prior to loading the data file. The reason we need to do this is HDFS is a distributed file system, and so not one place stores one specific file. Therefore, when we copy the data into HDFS, we need a subfolder to hold those contents. So from user directory, which is my last name, and the main data folder called ndata, we're going to make a new directory and create a new subfolder called sales_rec that will house the data sales_rec CSV file as a distributed file. Now that we have the subfolder created in HDFS, we need to take the actual CSV file and move it into our storage bucket and then into our cluster. So to do that, we upload the CSV file into the storage bucket in GCP. And then through our SSH terminal, we're going to copy that file from the storage bucket to our cluster. So first, we create the command line through ndata, the folder that we want to copy the file into. And then we use this command prompt right here, which says that we're going to copy from our storage bucket, ADTA 5240 Goodwin, and then I give the location of the storage file, and we're going to copy this file right here, sales_rec.csv. And we can see the screenshot that we do copy it, and one file is put into our cluster. Once the file is in our cluster, we want to make sure that it's in our cluster. So we're going to use a Linux command, ls-l, and we're going to observe all the contents in the ndata folder. And we can see right here that in fact sales_rec.csv was placed into the cluster. Once we know the file is in our cluster, now we want to move it into the HDFS subfolder that we created. So we're going to use the put function, and we're going to put our CSV file into that subfolder. So now it will become a distributed file in the HDSF username directory for us to use later. Now before we move on to creating any type of schema, we want to make sure that the item is actually in our HDF folder. So HDFS, DFS-ls, and then giving the file directory name all the way to the subfolder sales_rec, we can now see right here that sales_rec.csv is now a distributed file in our subfolder. We can now proceed with moving into Hive and creating a schema. To access the Hive command prompt, we're going to use beeline command prompt. And so to connect to Beeline and begin creating our external table, the command prompt beeline-u jdbc:/hive2: /localhost:10,000 is going to connect us to a Beeline prompt, and anything we enter in from here will now allow us to interact and work in Hive through our SSH terminal in our cluster. So now that we're connected to Beeline command prompt in Hive, we can start creating a table. So the first table we want to create is a simple schema, external table in Hive, and all we want to do is display the first couple rows, or in this case we're going to display the first 10 rows to get an idea of what our feature labels are so that we can create a well-defined schema. And we're also going to take a look at our data types. So the way we're going to create this table is we're going to create an external table named salesrec5, row format delimited, stored as a text file, and then we give the location of where to find the file contents. We can see in the screenshot that no rows were affected, the table was in fact created, and now we're going to display the first 10 rows. So to display the first 10 rows, we use the command prompt select, and then we use the star from, and we're going to give this table name, and then we want to limit it to 10 followed by a semicolon. And the reason we want to see the first 10 rows is that there's kind of a special note to talk about here. Before we put this in, we did realize that in the product name, commas were used. So if we create a well-defined schema, and if we parse on the commas, then some of our values would not be correct. So what happened was we needed to go back in, either using OpenRefine or in this case, I used Excel, and we went back and we wanted to replace all of the commas in the product name with something else that wouldn't parse, such as, you can see the highlighted portion, a semicolon. And so now all the product names that contained commas previously now contain semicolons so that the parsing was accurate. So that what comes after it, which is sales, will remain intact and give us a proper output later on in our queries. So this would be called data cleaning, and happens very often in the data transformation process. So here's a quick overview of what it would take to clean the data before we upload it into Cluster. One important note is once it's uploaded into HDFS, it's now a distributed file. So you want to clean the data. In this case, we clean the data before we upload it into the storage bucket, copy it into the cluster, and then use it as a distributed file in HDFS. So now we're ready to start creating a well-defined schema in Hive with our data set. So to create a well-defined schema, external table in Hive, we're going to use the first couple rows we saw in the simple schema, and we're going to take those feature labels and we're going to define them with the data type right here. So we create external table if not exists, and we're going to name it sales_rec_3. And so now here are all the feature names. The ones that I do want to bring the attention to would be sales, quantity, discount, and profit. Also, postal code. Postal code could be used as a string or an int, but sales was used as money, currency, and so we labeled that double, which is a double float, giving 2 decimal places after the decimal. The quantity was an integer, the discount was a double float, and the profit was a double float. And so defining these, we can now go ahead and say that we want all fields to be terminated by comma, which means we're going to parse on the comma, and the product name will stay intact as we described in the slide above. So here we can see how we entered our well-defined schema into Hive using Beeline, and when we hit enter, no rows affected, the table was created, and we want to ensure that the table was created. So we're going to show tables in Hive, and the show tables semicolon displays all the tables created. So here are prior tables from the class plus from the final project, and we can see our simple schema, which is SalesRec5, and our well-defined schema, SalesRec3. So the tables are in Hive and ready to be used for queries. So the first query we wanted to return, we wanted the top 5 states with the most amount of customers, the most number of customers. So we selected the state and we counted the customers and then gave that a new label as top customers from our well-defined schema. Then we grouped by the state, which all the counts were now grouped by state, and then we want to order by top customers, which is the new column that we gave the count of total customer IDs by state, and we want to order those by descending. And because we group by state, it's now going to list all the states in descending order from the greatest number of customers shopping to the least amount of customers shopping by state. And then we only want to return the top 5 states. So if we return the top 5 states, we want to limit this to the top 5. So limit 5 returns top 5 descending by top customers. And you can see that California, New York, Texas, Pennsylvania, and Washington were the top 5 states that had the most customers. One more important piece of information to note is that it tells you how many rows were selected from your query and how long Hive took to process this query. And that's going to be important when we get to part 4 and we start comparing speeds, processing speeds between Hive and Spark SQL. The second query that we wanted to return, we wanted to know what were the top 10 zip codes that had the most amount of sales in them. In other words, what regions were most profitable. So to get this, we selected the postal codes and from our well-defined schema, and then we summed the sales. So we want the total sales, which gives us the largest amount of sales, and we gave it a new name, top sales, and we took this from our well-defined schema. If we group the top sales, or the amount, the sum of sales, by each postal code, and then we order these postal codes by the amount of sales, also known as top sales, in descending order, it will give us a list from greatest to least of which postal codes had the most amount of sales in their region. And in this case, we wanted to limit it to the top 10 postal codes. So limit 10, execute the query, and we can see the top 10 postal codes and how many sales they had for each one, the total amount. We can also see down here that 10 rows were selected and the time it took for Hive to produce this result. So now in part 3, we're going to run the exact same two queries, but we're going to run them in Spark SQL from the well-defined schema that we have stored in Hive Metastore. The great thing about Spark SQL is that it can access Hive Metastore and then use the contents of that to run its own queries. So the first thing is we want to start the Spark SQL command prompt. And you can see that in order for this command prompt to actually work, Spark SQL must connect to Metastore first. And we can see that down here, that as we enter Spark SQL in the command prompt to try and initiate the command, that it's trying to connect right here to Metastore, and it will not initiate the command prompt until connected. So once Spark SQL command prompt is initiated, we can see up here that we are connected to Metastore, and now we want to see the tables that we have access to. So show tables, semicolon, and it shows us all the tables in Hive Metastore, the same tables we used in Hive, we now have access to in Spark SQL. So now with the well-defined schema, SalesRec3, that we've created in Hive, we're going to access that with Spark SQL, and we'll run the exact same query to get the top number of customers for the top 5 states. And so again, we select state, we count the customer ID to give the total count, and we're going to label this as top customers from our well-defined schema. We group them by state, we order them by top customers in descending order, and down here we can see that we have the top 5 states with the exact same values we received in Hive. The noticeable difference is the time taken. We fetched 5 rows and we did it in less time using Spark SQL. Likewise, with the second query we ran in Hive, we're now going to run the same query in Spark SQL. And we want the top 10 zip codes with the largest amount of sales. So we select postal code, sum the sales, give that another name. From our well-defined schema, we're going to group all the total sum of sales by postal code. We're going to order it by the top sales in descending order. And again, we can see the same postal codes, same zip codes with the same values that we had in Hive. And so nothing's changed other than it fetched 10 rows, but it did significantly less time. So now we move on to part 4, comparing performance between Hive and Spark SQL. So here's a table from the report that gave the comparison in time of how many rows were retrieved with our query and the time it took between Hive and Spark SQL. So for the top 5 states that had the most number of customers, in Hive it took 20.146 seconds, in Spark SQL 20.581 seconds. Spark SQL was almost twice as fast as Hive. The top 10 postal codes with the most amount of sales took 20.538 seconds in Hive and 4.857 seconds in Spark SQL. That's more than 4 times as fast as Hive. So let's talk about why. So here are the differences in the processes of using a query in Hive versus Spark SQL. In Hive, the user gives the query command, enters Hive server engine. It converts the data to be processed by MapReduce. MapReduce maps the job into smaller tasks. HDFS assigns data or worker nodes to the smaller tasks. The execution of the query is then passed back from the cluster nodes in HDFS to Hive server for the output. In Spark SQL, we use in-memory processing, or RAM, to process the data from Metastore, and we skip that entire loop and the query is returned to the user without MapReduce or HDFS, therefore being much faster than Hive.